Hello everyone, welcome back to the lectures and introduction to multi-engine systems. In the previous lecture, we introduced the topic of Lyapunov stability. However, we ended the lecture by discussing an example of a pendulum system. We saw that in that particular example, while the system was the equilibrium point, which was the origin, was actually asymptotically stable. However, for the given Lyapunov function, we could not really arrive at that conclusion. In today's lecture, we'll probe that particular aspect a bit more, and towards that, we will introduce something that's known as Lassalle's invariance principle. We'll also discuss how we can design Lyapunov functions for linear systems, thereby allowing us to, sometimes if required, linearize a nonlinear system about the origin and apply those same concepts. So let's get started and see how we can go about doing it. Let us start the example with a quick recap of the damped pendulum system that we discussed before. This was our pendulum system, and the state space equation governing the motion of the pendulum is as given here. So the Lyapunov function that we had chosen took this form, and we see here that the derivative of the Lyapunov function along the trajectory is equal to this value, minus p times x2 divided by ml squared. And we see that this derivative is always less than or equal to 0, from where we could straightforwardly conclude that x equals 0 is a stable equilibrium point. However, we also know that not only is this origin a stable equilibrium point, it is also an asymptotically stable equilibrium point. However, using the Lyapunov function that we have chosen here, we are unable to comment on that. So how can we possibly arrive at that conclusion in the sense of Lyapunov, that the origin is asymptotically stable? To do that, we'll now introduce something that's known as Lassalle's invariance principle. Lassalle's invariance principle says the following. Again, let us continue our discussion on an autonomous system. So we say, consider an autonomous system x dot equals f of x, where f is locally Lipschitz over the domain D. Then let omega, which in a given space, be a compact set. Compact set simply is a set which is closed and bounded. Which is positively invariant. What do we mean by positively invariant? It means that once the trajectory enters omega, it remains in omega. It cannot escape for t. Let's make this a bit more precise. We say that once the trajectory enters omega at some t equals t bar, then it remains there for all t greater than equal to t bar. Okay, so this is now our invariant set. What we also have is a Lyapunov function. We have a Lyapunov function. So we discussed earlier what are all the properties that a Lyapunov function V must satisfy. So I will not repeat it in this lecture. That's covered in details in the previous lecture. We have a candidate Lyapunov function V, and this Lyapunov function satisfies the following. V dot is less than or equal to 0 in omega. Okay. All right. So we know that V dot less than or equal to 0. So all those x which satisfy this condition, they remain in omega. That we know. Furthermore, let's define yet another set which takes the following form. E be the set of all points in omega where V dot of x is equal to 0. Furthermore, let's write it here. Let M be the largest invariant set in E itself. So a quick recap of what do we have so far. We started again with a standard system, which is autonomous. For that system, we defined a set omega. The property of this omega set is that it is positively invariant, meaning as soon as the trajectory enters the set, it remains there, it cannot escape. Inside of that set, so we say that the Lyapunov function for all those values of x for which V dot is less than or equal to 0, it lies in omega. Of all of these values of x which satisfy these conditions, we pick the largest set E. Or rather, we pick the set of all points in omega where V dot is equal to 0. Now, let M be the largest invariant set inside of E itself. This allows us to now state a very important property. We can say that every trajectory starting in omega approaches M as t tends to infinity. So this is the statement of Lassalle's invariance principle. What have we shown? We have a Lyapunov function now which satisfies V dot is less than or equal to 0 in the given set omega. All of the x values which satisfy this condition, from there we pick only some of them such that for those values of x, V dot is equal to 0 and we call that set E. Now inside of E, we take the further largest invariant set. And what we definitely know is if we somehow enter this region omega, then the trajectory is guaranteed to approach the set M. Let us try to understand this theorem using the pendulum example that we saw before. So this is our system. In this particular example, let us try to calculate what is the largest invariant set where v dot is equal to 0? V dot of x is equal to 0 implies, sorry, this should be x2 squared. This only occurs when x2 is equal to 0. So remember that we have now entered the set E. So let's see here. E lies inside. So when x2 is equal to 0, we have, so this is what we are starting with. We have x2 is equal to 0, and we'll now try to figure out what happens to the other states. Here, x1 dot is equal to x2, hence this is equal to 0, and x2 dot is also equal to 0. The reason being that x of t belongs to E. Owing to this, it doesn't change its state. Hence, x2 of t continues to be equal to 0. Since x2 doesn't change its state, we know that x2 dot is also equal to 0. So we now know that x2 dot is equal to 0. If that happens, then we know that we can see here the expression of x2 dot is given by this, and here the second term already goes to 0 as x2 is equal to 0. Hence, what we are left with is, so let's write it, this implies minus g by L sine x1 minus 0 is equal to 0, which implies sine of x1 is equal to 0. In the case of a pendulum, let us draw a rough sketch of it. In the case of a pendulum, this angle is theta. Sine, so, and x1 is equal to theta. So sine theta goes to 0. This implies that theta, because we cannot have the angle phi in this case, so theta becomes equal to 0. So we directly write here that this implies x1 is equal to 0. Hence, what did we get here? We see that ultimately, if v dot is equal to 0, this implies that the largest invariant set M inside of this E it consists of this point 0, 0, and 0, 0 is our origin. Again, the Lassalle's invariance principle says that every trajectory starting in omega approaches M. Hence, this implies the trajectory approaches the origin, which implies the important conclusion: the origin is asymptotically stable. So using the Lassalle's invariance principle, we are now also able to comment on this property. So even if v dot is negative semi-definite, still Lassalle's invariance principle allows us to arrive at such important conclusions. Now we'll look at something that's known as Lyapunov's indirect method for stability. This is the indirect method. So what do we mean by the Lyapunov's indirect method? So as before, we start with the same setup. Consider an autonomous system x dot equals f of x, where f is locally Lipschitz over the domain D. Next, let A be given by the matrix dou f by dou x evaluated at x equals 0. So A is an n cross n matrix. So how does this part evaluate to an n cross n matrix? It's because f that we have is again a vector from f1 to fn. And in this term, every row is evaluated as, dou f1, let's say the first row, or we can write the ith row of A is given by dou fi by dou x1, dou fi by dou x2 up to dou fi by dou xn. This is the ith row of the matrix. And since there are n number of fi's, so we can thus construct an n cross n matrix in this manner. Coming back to the result. Now we have constructed this matrix A. How can we talk about the stability of the equilibrium point at origin? The result goes as follows. Origin is asymptotically stable if the real part of lambda I, what is lambda I? Lambda I is the ith eigenvalue of the matrix A. If real part of lambda I is strictly less than 0 for every lambda I belonging to the spectrum of the matrix A. This is the first result. The second result says that the origin is unstable. When is the origin unstable? It is when the real part of lambda I is greater. Okay, let's write it better. Or let's continue that way. Real part of lambda I is greater than 0 for one or more eigenvalues of A. So this is the Lyapunov's indirect method to check the stability of an equilibrium point. What it says is, suppose we linearize, so this process is known as linearization. Suppose we linearize the nonlinear system about the origin. Through that, we get this matrix A. So very close to the origin, now we assume that the nonlinear system behaves like, so let's write it, close to the origin. The nonlinear system can be represented using this linearized version given by this. So instead of writing equals, let's write this. So now the stability of origin depends on the eigenvalues of A. If all of its eigenvalues are less than 0, then we know that the origin is asymptotically stable. And if even one of the eigenvalues is greater than 0, then origin becomes an unstable equilibrium point. If we are directly starting with a linear system, that means we can straightforwardly apply these properties. Let us try to understand this through an example. Consider the system given by x1 dot is equal to x2 and x2 dot is equal to minus x1 plus x1 squared again. So this is a nonlinear system given to us. So let us firstly evaluate its equilibrium points. The equilibrium points of the system are given by setting x1 dot equals 0 and x2 dot equals 0. Setting x1 dot equals 0 simply gives us x2 equals 0, and setting x2 dot equals 0 gives us minus x1. So here what we can do is we can take x1 comma common. So what we are left with is 1 minus x1. So we set this to 0. This again gives us x2 equals 0. And x1 now can be either equal to 0 or equal to 1. Hence, we have two equilibrium points. Given by 0, 0, the origin, and 1, 0. So these are the two equilibrium points. We are interested in studying the behavior of the system. We are interested in studying the stability of origin. Hence, what we'll do is we'll linearize the system about the origin. Let's see how we'll go about linearizing it. For that, we'll compute something that's known as Jacobian. So going back to this matrix A, it's also known as the Jacobian matrix. Or rather, this is what it is known as most of the times. So let's find the Jacobian matrix. Sometimes it's also denoted as J, but to be consistent with annotations, let's write A. Then A is given by dou F1 by dou X1 and dou F1 by dou X2, dou F2 by dou X1 and dou F2 by dou X2. The entire matrix is evaluated at x equals 0. So what is F1? Just for our ease of reference, let's write it here. F1 is simply equal to x2 and F2 is equal to minus x1 plus x1 squared. Then dou F1 by dou x1 is 0 and dou F1 by dou x2 is equal to 1. And dou F2 by dou x1 is equal to minus 1 plus 2x1. And the second term here, dou F2 by dou x2 is 0. And this is evaluated at x equals 0. Hence, after linearization, we get that a Jacobian matrix turns out to be 0, 1, and then we get here minus 1 and 0. Let us try to understand this through an example. Let x1 dot be equal to x2 and x2 dot be equal to x1 plus x1 squared again. Let's start by finding out what are the equilibrium points. The equilibrium points of this system is given by setting x1 dot equals 0 and x2 dot equals 0. Evaluating both, we get, when x1 dot is equal to 0, we get simply x2 equals 0. And by setting x2 dot equals 0, we get x1 plus x1 squared equals 0. So it implies we can take x1 common and we have 1 plus x1 equals 0. This means we have two possibilities of equilibrium points. The first is obviously 0, 0, and the second one is minus 1, 0. So these are the two possible equilibrium points of the system. Now we compute the matrix A, which is also known as the Jacobian matrix. It's obtained after linearization about the origin. When we linearize about the origin, the A matrix is given by dou F1 by dou X1, dou F1 by dou X2, similarly dou F2 by dou X1 and dou F2 by dou X2. And since it is linearized about origin, we have to write x equals 0 here. Now, just for our ease of reference, let's write it here that F1 is equal to x2 and F2 is equal to x1 plus x1 squared. Then the first term, dou F1 by dou X1 simply 0. The second term is equal to 1. And the third term, dou F2 by dou X1 is equal to 1 plus 2x1. And the last term again is equal to 0. Now, when evaluated at the origin, this matrix simply becomes equal to A equals 0, 1, 1, and 0. Then how do we check the stability of the origin? We evaluate the eigenvalues of A. So if we solve it using the standard expressions of determinant of lambda I minus A equals 0, we can get the characteristic polynomial and calculate the eigenvalues from there. So for now, let me directly write the eigenvalues. They are equal to plus 1 and minus 1. So what is the indirect method of Lyapunov say? It says that if the real part of the eigenvalue is greater than 0, even for just one of the eigenvalues, then origin becomes an unstable equilibrium point. Meaning here, we can directly conclude that origin is unstable. So this is how we evaluate the stability of origin under the indirect method. Let us now quickly see how can we easily evaluate Lyapunov functions or easily determine suitable candidates for Lyapunov functions in the case of linear systems. Linear systems. Or let's write Lyapunov stability for linear systems. Let us consider the linear system x dot equals a of x. Now, let us consider a positive definite matrix Q. Obviously, this is also a symmetric matrix. Then what we do is we solve the equation P times A plus A transpose P is equal to minus K. In this equation, the only unknown is P. We know what is A, it is the system matrix, and Q is what we have chosen here. So we solve for P. Once we have the P matrix, then the Lyapunov function is given by V of x is x transpose P of x. Note that the P here is also, it satisfies a few properties. P is a symmetric matrix. Then the result for stability goes as follows. The condition for asymptotic stability. It says that if P is positive definite, remember that P is a solution of this equation. If the P turns out to be a positive definite matrix, then origin is asymptotically stable. We can write then origin is asymptotically stable. In other words, what happens is all the eigenvalues of A. So if you remember, we start with the matrix x dot equals AX. Then from our knowledge on the basic control theory, we know that the system is stable only when all of the eigenvalues are less than 0. Hence, if you're able to find a positive definite matrix P, then the system is asymptotically stable. Hence, all of the eigenvalues of the system matrix A, their real part, so rather we should write the real parts of the eigenvalues of A must lie in LHP, which means the left half plane. So this is Lyapunov stability for linear system. And this is a very easy way in which we can compute a valid Lyapunov function. We know that if we can find a valid Lyapunov function, the system is, by definition of a Lyapunov, it is stable. Hence, the same is written or mentioned here. Let us now quickly see an example. But before that, let me highlight yet another property, which can be thought of as the converse of this. So let me just mention this as a converse theorem. It simply says that if the real part of lambda I is less than 0 for every lambda I belonging to the spectrum of A, then for every Q equals Q transpose, meaning symmetric matrix, let's write for every positive definite matrix Q, there always exists a positive definite P such that PA plus A transpose P is equal to minus Q. So this is the same thing stated conversely. Let's try to understand this through a very quick example. Let us consider the linear system x dot equals ax, where A is given by -1, 4, and 0, and -3. Multiplied by x1, comma, x1 and x2. This is our x. Then the eigenvalues of A are equal to -1 and -3. Now, we are interested in calculating, or we are interested in finding a candidate Lyapunov function. So what do? We start by saying we choose a Lyapunov function. We choose a quadratic Lyapunov function. It's because x transpose px is a quadratic form. So we say that we are choosing a quadratic Lyapunov function given by x transpose px. P is some square matrix, which is positive definite, if we want the system to be stable. And we already know that all of its eigenvalues are in LHP, so we can find a positive definite P. We choose Q as the identity matrix because we know that the identity is a symmetric matrix, which is also positive definite. Hence, matrix P must satisfy the condition PA plus A transpose P equals minus of Q, which is minus of identity. So the entries of P are P11, P12, P22, so P21 and P22. And A matrix is -1, 4, 0, and -3. And A transpose is equal to -1, 0, 4, and -3. And P is equal to and this must be equal to identity or negative of that. Let me shift this slightly here so that I can accommodate identity. Zero and -1. This gives us the so know that P12 equals P21 because we want it to be a symmetric matrix. So let's write that somewhere here, that P12 equals P21. Upon solving it, we get matrix P as being equal to half, 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 and 5/6. And the candidate Lyapunov function becomes simply X transpose P of X. So this is how we can calculate quadratic Lyapunov functions for linear systems. Just a quick note on its origin. Why does it all work out this way? Well, it's quite simple. So suppose we start with the candidate Lyapunov function given by X transpose Px. Let us start without knowing what is Q. Now, when we take a derivative of this, we get X dot plus X transpose P X dot. Now we know that X dot equals A of X. Then we simply substitute it here. AX transpose PX plus X transpose P AX. This becomes X transpose A transpose P times X plus X transpose PA times X. We can take X transpose common on both sides and write A transpose P plus PA times X. Ideally, we want V dot to be negative definite. Hence, let us say we want it to be less than 0 for every X not equal to origin. In that case, what do? We force it to be equal to some minus Q, where Q itself is positive definite. Hence, minus of Q is a negative definite matrix, which solves our purpose. Hence, any matrix, so we start by choosing some Q, which is a positive definite matrix, and then we try to calculate a P which satisfies this equation. If we can find a suitable P, then we know that our job is done. So this is this is why we do the calculations mentioned here for the case of linear systems. With this, we end our discussions on nonlinear systems, nonlinear dynamical systems. In the next lecture, we'll see some applications of multi-agent systems, and we'll use the tools of graph theory and nonlinear dynamical systems to see how we can actually design distributed algorithms for multi-agent systems. Thank you.